today I will present one extension of SYCL called joint matrix. So when it comes to programming abstractions, users are usually looking for the right level of abstraction. So we can find things from the frameworks like Tensorflow, PyTorch, to libraries like oneDNN, oneDNN, and then finally, so you can go from that level to CUDA, SYCL, and then intrinsics and assembly. So we are always looking for the right trade-off between these levels of abstractions, and the goal usually is getting performance. So the lower you go, you get more performance, but then and you want more control over the hardware, but then it becomes harder and hard to also make it portable across different hardware. And that's why there are many related work to the work I present today. So there is another abstraction that belongs to SYCL called ECMD, which is even lower level, dedicated for GPUs. We find things like Triton, which is like the scope that, or the granularity that the programmer uses is usually a work group. Cutlass, Sanjeev touched up a little bit on that. So it's a templated library, and you can do all sorts of things. I would say, so it's similar to things like oneDNN, but it lets you call library calls from the kernel, which is really nice. So oneDNN and oneDNN, so these are libraries that you can call only from the host. There's something called CUDA WMMA. That's an extension added to CUDA, and it lets you program directly the NVIDIA Tensor Cores. So in the middle of all this, we created a SYCL joint matrix, and the idea is to give a unified matrix interface. It lets you program and run, and it gives you direct control over Intel AMX, which is the matrix extension added to Intel CPUs, Intel XMX, which is the matrix extension added to Intel GPUs, NVIDIA Tensor Cores, and AMD Matrix Cores. The status as of today, so the unified interface, which is the API I will present today, that can run on these different hardware. So it is available starting oneAPI 2023.1 release. So it has been a couple of years already. And since then, we add more extensions, better optimizations in the compiler. It runs faster. And also the status is we participated in the development of SPIR-V cooperative matrix, and we fully transitioned to that extension in the compiler. So now if you compile a SYCL program that uses SYCL joint matrix at the SPIR-V level, you will see this standard extension called cooperative matrix. So starting 2025.1 release. And the goal also has been to get to the best performance, even like better than oneDNN. But as of today, we have we can deliver comparable performance to oneDNN. But of course, so it's not a black box function call like you do in oneDNN. You get the flexibility and the freedom to apply any custom optimizations you have or your specific workload requires, especially with regards to kernel fusions. And then, so I will talk about this during the talk, but so in order to get to this comparable performance, you need to do lots of performance tuning. And we also, so to help users with this tuning, we make it open. We make the kernel that we develop open source to people. So they, even if your workload differ in terms of activation functions, the what you do besides the GEMM, which data type you are using, but these kernels that we provide can help you port or specialize your application. So I have a simple outline. I will talk about the hardware, the matrix hardware that we have, that Intel provides. I will talk about the API and some ideas for tuning. So can you confirm, do you see there is a black thing on top of my screen? Do you also see it? Okay, it went away. Never mind. Okay, so on the right-hand side, I will talk first about Intel XMX. Let me just check. Yes, Intel XMX. So Intel XMX is the systolic array added to Intel GPUs, and it has been added to both the client and the data center GPU. So on the client side, which is the left-hand side, so the code name for this is Battle Mage or BMG. So the XMX unit, or the systolic array, is the little light blue box here, XMX. So you have 8 in total in each XZ core, and then you have 4 XZ cores inside the slice, and you have a total of 5 slices in Battle Mage GPU. So in total, you will have 160 XMX engine that you should use and benefit from for your GEMM applications. On the right-hand side, we have the Pentavacuum, or the data center GPU. And in this case, so if we just take one tile, here we have 2 tiles, but if we take one tile, there are 4 slices in each tile, and then each slice has 16 XZ cores. And similarly to Battle Mage, an XZ core has 8 XMX units. So in total, in one tile, you have 512 XMX engines. So of course, you can use oneDNN, and transparently, oneDNN will use this for you, or you can use SYCL joint matrix to directly have access to this hardware. The data types that you can use with Intel XMX are bfloat16, half, TF32, int8, and even int4, like 4 bits integers. You cannot do things like double, for instance. For that, you will have to use the EUs, or the vector units. On the CPU side, and mostly on the data center side of CPUs, in the tech talk this morning, you guys use SPR, or what we call Intel Xeon processor. And also there is a successor, which is the Intel Xeon 6 processor, or the code name is Granite Rapid. So we have 2 now, Sapphire Rapid and Granite Rapid. They both have Intel XMX unit, which is embedded with the core. So in each core there is an Intel AMX engine, and so I think the only difference between Sapphire Rapid and Granite Rapid with regards to Intel AMX is the data types. So you can do half now with Granite Rapids, but with Sapphire Rapid you can only use bfloat16 and int8 data types. So with SYCL joint matrix, the data types are only the ones that the hardware supports. So we don't provide like fallback or emulation. So we use the matrix hardware. So on the picture also here, I have the tiles, or the 2D registers that Intel AMX has. So there are 8 in total, 8 kilobytes in total. For each core, and these are separate from the core. So if you are using some vector operations, these will be using the vector registers. Intel AMX will be using the 2D or the matrix registers. So the users have to take care of, be aware of this separation of registers. Okay, so let's dive into the API. So the first extension, or the first element in this API is the new data type, which is joint matrix. So joint matrix is a new data type added here, it has multiple templated arguments group, which specifies the memory scope of joint matrix, because the matrix is not owned by each work item like how you would do normally in a SYCL program. It is shared for the work items within the work within the group that you specify in this case. So far with the hardware we have, the native group is subgroup. So you have one subgroup sharing a matrix. So in the example, you will see here that I'm using a subgroup. And then you can specify what is the data type of the matrix, what is the use in the GEMM. Is it A, matrix A, B, or C, or the accumulator in the GEMM? And that's important to give hints to the hardware or to the compiler to optimize layouts for the matrix hardware. You also, so you can specify what is the shape of the matrix, so what is the number of rows, what is the number of columns. The layouts can be specified on the matrix, and this is the memory layout on the matrix or in the operations. I will show that in a second. So, okay, so we went over that. So the layout is the memory layout. It's row major, column major. These are the main layouts that users are using. Now, what do you do with this new joint matrix data type? So you can apply memory operations. You can fill the joint matrix, so you can fill with some value. So if you want to bypass the memory operations, you can fill directly, and that will be like a move operation directly into the register. The load will load from memory, so you will find a pointer here. So you load from memory to the joint matrix, and you specify the layouts there. Joint matrix store, you store from, so once you are done with your computations, you store from the joint matrix into the memory. And the prefetch, that's something we added recently, which is important for performance on both BattleMage and PentaVacuum. So you prefetch, it helps you prefetch from memory. So I have a pointer here to cache, and you specify which level of the cache using the properties. And of course, yeah, it's worth mentioning. So you use prefetch if you are not using the shared local memory. So if you are using the shared local memory, will behave like a prefetch if you are using that. The second set of operations, so besides the memory operations, you can apply compute operations. So the main operation is joint matrix multiply and add. So MAD stands for multiply and add. That will do A, so joint matrix A times B plus C, return the value into another matrix D. And then how do you do, usually after GEMM, you are going to apply activation functions, element-wise operations, what Greg talked about, like quantization, dequantization, where you convert between data types. And for that, you can use, so all this can be used in a single API called joint matrix apply, which lets you apply a function on each element of the joint matrix. So you can apply, here we have two flavors, one where it takes one joint matrix, so it returns the result into the matrix, but then also it can take two matrices, so you can apply something to a matrix and then it returns the value into a second matrix, and you can do all kinds of things with apply. The last API is joint matrix copy. It lets you copy between two matrices. The main use case in this case is to convert between the use, because sometimes, so you did a GEMM, the returned matrix is an accumulator matrix, but now you want to use it in a second GEMM as an A or B matrix, so you need to convert between the uses without trips to memory. So in this case, you can use joint matrix copy. I have an example here. So on the left-hand side, I have an example with joint matrix. So this is a GEMM. This is how you write like the very naive GEMM operation in SYCL, and this is within a kernel. So I'm not showing like the part where you create the queue, submit the kernel into the queue, how you manage your memory. You either copy from host to device or use unified shared memory to avoid that. So I'm skipping directly to the part inside the kernel. I'm going to apply a GEMM. So yeah, very naively, I have three matrices, A, B, C. So use is AB accumulator. I fill my matrix C with 0. I have the K loop, which is the sequential loop where I'm going to do the accumulation. I load A from memory, I load B from memory. I call joint matrix MAD. And then before I store the result, which is MAD C, before I call the store here, I apply some element-wise operation. So I can apply anything. Like in this case, I multiply with alpha, return the results into MAD C, and finally I store. I have a very important note here, which is parameters are not portable. So while the API is portable, but of course, the arguments or the shape of the matrices can be non-portable. We try, so we have, especially to migrate from CUDA, we support some cases where you don't need to change your code at all. But for the most part, these parameters are tunable. You need to look at the query in this case. So we have a query to program these arguments. On the right-hand side, I have the CUDA WMMA extension that uses something called fragments for a matrix, and it is very similar. So a fragment can be seen as a equivalent to joint matrix. There is a fill operation, load, store. The main difference is how they do the element-wise operation. So in this case, num elements is how many elements per work item, and then yeah, so there is this variable x that gives you the array per work item. So you have to think in terms of like what is the portion per work item and do the operation. Whereas in this case, so joint matrix apply will do that yeah, explicitly. Yes, so of course the main difference is that the code on the left will run on Intel AMX, so Sapphire Rapid, Granite Rapid, Intel XMX, Battlemage, PVC, NVIDIA Tensor Cores in all the GPUs that support that, and AMD Matrix Cores. And if you, so you can start from scratch, or you can use a CUDA application and migrate it using the DPC++ compatibility tool, or what we call also cyclomatic, and it will also handle the joint matrix parts or the WMMA parts and convert them to joint matrix parts. So the code I showed before, so I said it's a very naive code. You won't get any good performance from this code. So you need tuning. And the main tuning that we do on every code, so it's not specific to matrix hardware, is the blocking. So you want to make your big data into tiles, load into cache, or use shared local memory, and then do subgroup operations. So that's another high level of hierarchy. So you have to think how much data I'm going to make a work group execute, and then how much data I'm going to make a subgroup execute before you think about what is a joint matrix shape. And usually a joint matrix shape can be the same as the subgroup shape, unless you really want, unless you have an activation function. There is an example, for instance, like if you are using a softmax that needs a lot of registers. So in this case, yeah, you want to go even smaller on the shapes. So and you will diverge from the subgroup shapes. So I show an example here. This is the naive code on the left-hand side that I was showing. On the right-hand side, so you have to think in terms of what is my global range? I don't need all these work items because the work items will cooperatively run the matrix operations. So I need less, so I have to, that's why I have a division here. Same for the local range, how many elements per work group I need. And again, there is a division because you need less work items. So for the same reason, the joint matrix shapes can change. So they can be higher, they can match the subgroup tile. Yeah, so that's it for the most part. So you do this blocking. I remind this in the table below. What is the work group tile? What is the subgroup tile? So to give you a small idea, like for shape, for GEMM shape, that is 4K by 4K by 4K, which is the MNK dimensions. Like the tile that works best on PentaVacuum and BMG as well is like 256 by 256 by 32 in this range, and then the subgroup tile 32 by 64 by 16. So you can see how it's in this range. But of course, the moment you start adding, if it is a GELU or something else, or softmax, it's completely, so the moment you start fusing those kernels, you will have to rethink these shapes. So more tuning, we need more tuning to do to get best performance. On PentaVacuum, we find that prefetch helps a lot. So prefetch will, in my example here, I'm prefetching into level 1 cache. So we needed to do it for both A and B, and we use for that. So there is an API to do that for you, which is joint matrix prefetch. And then in SYCL, we have something called annotated pointers, where you can add the cache information on the pointer to say, that's where I want my load to go. Do I want my load to bypass L1 cache? Do you want my load to pass through L1, L3? So there are multiple modes. So one example, for instance, that came from a real application where they want to bypass the cache for matrix A. So in this case, in the load, PA here is an annotated pointer. And the annotated pointer use your memory matrix A, but then you can specify the property to say N cache for L1. Yeah, I see that I don't have much time, so I'm glad I didn't put performance data, but I'm happy, you know, if anybody is interested, I'm happy to share more information, share the kernels, how we can incorporate here your kernels with the kernels we have. And we have, I started a repo for that, and I'm working on adding more kernels. So I talked about softmax a lot because that's the one I'm working on right now. I'm working on how I can fuse it with GEMM and get the best performance. So just to reiterate, so SYCL and SYCL joint matrix, it will work on all these hardware and on all these matrix hardware with just the same code. Of course, you have to tune the shapes using the query. And then we are using the SPIR-V cooperative matrix underneath to represent the SYCL joint matrix. We got comparable performance to oneDNN, and we are working on more like better results. We have some successful stories, especially with CUDA migration. People migrate their code from CUDA to be able to run on all these different hardware. Yeah, and that's it.
Dounia, yep. So we have some time for questions. One question is posted by George. Can you discuss what the current memory interface is? Is this interface for HBM or something else?
Where did I, so it's not in Intel AMX or in the, I think I said unified memory. Yeah, I don't think I said coherent memory, but if you are asking about the unified memory, USM in SYCL, so that's something that lets you allocate data on both the host and the device, so you don't worry about creating accessors to get the data from the host.
Okay, George, you have any questions? Should I escalate to you, panelist, or? Okay, thanks, George. Any other questions from the attendees here?
Oh, yeah. So, okay. So there are, yes, it's the HBM.
There is another question by Geoff asking, do we have performance data and where one can look for?
So I have two types of performance data here. I have a slide that talks about the importance of fusion with the GELU kernel. So I show here the orange bar is when you fuse in the same kernel, and then the blue is when you have a kernel that does GEMM and then the other kernel that does GELU. And then I think we can generalize these findings to any other operation you are doing besides the GEMM. So we see a difference for small data shapes. And which is a trend in ML code. So the data are very small. So when you fuse the data, which is you fuse the kernels, which is the orange bar, the performance, so that's the speed up compared to the separation, the speed up is a lot, so the performance is a lot. So that's one performance data I have. And then the second one is comparing to oneDNN, because I said comparable. So I think it's nice to explain that more. Of course, you have to do like all the things I talked about, prefetch, so you have to add that to your kernel, because with oneDNN, it's one function call. So it's really, it's about what is your workload. Like we got a request recently, I want to use int 4, like 4 bits. People cannot do this with oneDNN today. So that's something, yes, you should go and use joint matrix, even though I haven't tested the performance for that data type. But so the comparable, if we look at 4K by 4K by 4K specifically, so it's about 95%. But then for small shapes, we get better results. For the big data shapes, which is less important for deep learning, but I know, like I have an idea what's wrong there. oneDNN, they do more, like you have to do more reordering of the data. That's something we don't do at all, actually. So, like they put data contiguously in memory before the loads or before the actual kernel, and that's something that can be good for inference, because for inference, so you do it once, and then so you call the actual kernel. So it doesn't make sense to do the reordering many times. But on the training side, you will have to do this reordering every time. So there are there are differences and many ways how to do things. On AMX, I think I should also talk about AMX, but I don't have a slide for it. It's the same story. So comparable results, but we are not doing the reordering that oneDNN is doing, which is, it turns out to be more important on the CPU than the GPU.